Okay guys, let's get started for today, and we're going to return to our discussion of the MOSFET. And as I mentioned last time, what I want to do here is give you guys just a visual image of how the MOSFET works. We're not going to try to go into deriving the actual equations. That's for other courses in semiconductor physics. Instead, our focus is on just seeing mentally what's going on, kind of get that picture in our mind, and then I'm just going to provide you guys with the equations, and then we're going to proceed from there. So let's once again look at our NFET, NMOS-FET. And as we mentioned last time, we have to look at this thing. This is a cross section, but there's also a width and a length. There is a length that goes along the length, or pardon me, along the direction of the board. And then there is a width of the gate area that goes into the board. And so, of course, I can't draw that, but that will go straight into the board. And so there is that third dimension that we can't see in this cross section. But as we're going to see later on, the width and the length are going to be essential to one of the equations when we start looking at how a MOSFET works. So here, let's begin by making a couple of observations about this. Now we notice I've got the source and the drain, but when I look at this circuit, really, why do I call one the source and one the drain? Because when we look at this, this is a symmetrical structure. There's really no difference. You could draw a line right down the center, and this would be kind of an XY mirror image of itself. So this MOSFET, the way I've drawn it, is a symmetrical device. What that means is what we call the source and what we call the drain are interchangeable, depending upon the polarity of the voltages we connect to those terminals. So what we're going to find here is, for this circuit, or for this device, we're going to see that current flow is going to be from the drain to the source. However, we're going to see for the PFET, positive current flow is from the source to the drain. It's going to be opposite. But it's going to be, in this case, drain to source, and we're going to see in a minute how that's going to work. Okay? So, let's look at this, and let's go through and start connecting this circuit to some things. And let's see how this device is going to work. So what I'm first going to do is, with my MOSFET operation, in order for interesting things to happen, I've got to connect sources to this device. So let's go ahead and do that. What I'm going to do first is the bulk, I'm going to ground that. Then I'm going to connect the drain, the gate, and the source to some sources of their own. So I'm going to connect a voltage source between the gate terminal and the source terminal. And I'm going to call this voltage VGS. Then I'm going to have a voltage, excuse me, and I'm also going to take the source here, and I'm going to ground that source too. So the source is grounded, but I've got a voltage source from that gate to that source. But the source terminal is grounded as well. And then I'm going to draw one more. Let me make a little room here. I'm also going to connect another voltage from the drain to the source, but since the source is grounded, I'm just going to connect it to ground. I'm going to call this VDS. Now I want to point out a convention I'm using here that you're going to see over and over again this semester. Notice VGS. VGS is the same as VG minus VS. This subscript minus that subscript. VDS is equal to VD minus VS. So when you see these double subscripts, what you're seeing is it's a shorthand way of me identifying a voltage drop between two terminals or two nodes in the circuit. So you will see this in the book, and you'll see this constantly, not only with MOSFETs, but we'll see it with BJTs as well. Okay? So let's begin. I've connected my voltage sources, and let's begin keeping in mind that I've got a P region underneath this gate, and just to remind everybody, this region here is between the gate and the region under here. This is SiO2. This is silicon dioxide. This is an insulator, in effect. It's glass. All right? So, let's begin first by assuming that VGS is equal to 0. And VDS is equal to 0. So I've connected the voltage sources, but I haven't turned them on yet. In this case, the MOSFET is in what we call cutoff. In other words, no current can flow. There's no voltages connected to the circuit, so since all the voltages are 0, nothing's going to happen. No current's going to flow. All right. Now note, all this region under here, this is all P-type substrate. So I've got P region that is separating these two N regions. And not just that, I've got N and P. What do I expect to happen between these P regions and these N regions? What do I expect to form? What type of region do I expect to form? A depletion region, right? This is no different than a PN diode. In fact, it's exactly the same as a PN diode. So what I'm going to find is this is going to happen. I'm going to have a depletion region is going to form between the drain and the bulk and the source and the bulk. So since the P substrate's lightly doped, we're going to have a wide depletion region in the P substrate, but the depletion region will be thin in the drain and source regions because they tend to be heavily doped, as we mentioned last time. So here we have depletion regions. Now this region underneath the gate, we give a name to that. Okay? What we're going to do is we are going to form what's called a channel. Now right now there is no channel. There's nothing here. Current cannot flow from the from this drain to the source region because it cannot go through that P region. It's like two back-to-back diodes connected oppositely from each other. One is always going to be reverse biased. So in this case, nothing can happen with this circuit or with this circuit the way it is right now, or this device the way it is right now. Okay? So we note that the P-type channel So the P-type channel separates the N-type drain and source regions, and it's literally like two back-to-back diodes. Okay, so this is uninteresting right now. If all the voltages are zero, nothing interesting is going to happen, but now we're going to start to make something happen. Let's now take and let's start increasing VGS. For now, however, I'm going to keep VDS the same. I'm not going to change VDS. That's going to stay 0. Okay. What's going to happen as I start to increase VGS? I'm making VGS more positive. Let's think about this for a moment. Okay, this terminal's grounded. The substrate, the bulk, is grounded. And I'm going to apply a positive potential to that gate. So what's going to happen? Got positive charge on this gate. So what is attracted by positive charge? Electrons. Okay, now look down at this P-type substrate. Holes are majority carriers, but there are still free electrons as minority carriers even in a P-type substrate. So what's going to happen is, as I start to have an increasingly positive voltage on that gate, what I'm going to find is electrons, the free electrons that are in that P-type substrate, are going to be attracted. And they're going to begin to accumulate underneath that gate. So those free electrons that are in that bulk, even though they're minority carriers, they start to get attracted. They start to accumulate. And the more positive I make that gate, the more electrons get pulled up underneath that gate region. So, as I make the gate source voltage more positive, at some point, so many electrons are going to accumulate underneath that gate that the region underneath the gate effectively transitions over from being a P-type to an N-type semiconductor, just because of all the electrons that are being attracted. So as VGS increases, an N-type channel is going to form beneath the gate. So what's going to happen is I'm going to have this. So many electrons get pulled underneath that right underneath the gate this turns into an N-type region. And now that N-type region connects the drain and the source together. Now this is strictly temporary. This is only because of the voltage being applied. If I took the voltage away, those electrons would scatter through the substrate. But for now, I have temporarily formed this channel because of that gate voltage. Okay? So here I have an N-type channel. And when does this happen? This happens when VGS reaches a certain critical voltage that we call the threshold voltage. This happens when VGS is greater than or equal to V sub little t. And I want to point out, this is not equal to thermal voltage with the capital T subscript. We've looked at this before in looking at diodes. This is threshold voltage. It's the minimum voltage required to form that channel underneath the gate region. Okay, so once this happens, and this region is formed, what I'm going to see is now this depletion region is going to extend all the way around. So now my depletion region goes all through the channel, connecting the drain and the source together. So now there is a path between the drain and the source, thanks to that channel. Okay? Oops. Now this channel, you'll also see that this is sometimes called an inversion layer. And why is that? Because we have, in fact, we've flipped the semiconductor from being a P-type to an N-type. We've inverted it. But we note that even though the channel is formed, there's still no way for current to flow between the drain and the source, but because VDS is still equal to 0. So I've formed a channel, but for now, there's still no current flow because VDS, there's no potential between the drain and the source. So nothing's going to happen. All I've done is I've created a path. Now what I'm going to do, quite predictably, is I'm going to now start to increase VDS. Now, some nomenclature we're going to need before we go to this next step. Right now, I've got the channel formed, I've got no current flowing, but right now, the MOSFET is no longer in cutoff. And the reason why is, I'm saying it's not in cutoff because now I've created a path for current to flow, even though VDS is still equal to 0. But once I form that channel, I say that this MOSFET is now in active or triode or ohmic region of operation. Typically, the book uses triode or ohmic, but you'll see other terms. Other textbooks will say that it's in the active region, and some will say it's in the non-saturated region. If you look in different textbooks use different terms for this condition. So the channel's formed, it is now possible for current to flow. You can kind of think about it as I've kind of flipped a switch. I've now created a path between the drain and the source. But I'm not calling it in cutoff anymore because now I have the ability for current to flow. So now I'm going to start to increase that current, VDS, or probably increase that voltage, VDS. And as I do, as I increase the voltage, well, I've got a path between the drain and the source. And what's predictably going to happen as I put a voltage across that region? Current's going to flow. So I'm first going to start to increase VDS. Let's first assume VDS is small. So with a small VDS, for now I'm just going to assume it's a small voltage. So VDS is small, drain current's going to start to flow. And that drain current, if I think about this from the viewpoint of positive current flow, is going to flow from drain to source. I sub D. So if that's positive, positive current flow is out the positive terminal, into the drain, into the source, and then to ground. So pretty basic. Now, as part of this, current is flowing, but we're still in the triode region. So we're in the triode region of operation. But something begins to happen. As VDS becomes more positive, then we note that the drain region becomes more positive. And what happens is that N-type channel begins to pinch off at the drain end, begins to narrow. So let me take that and I'm going to redraw this down here to basically try to clarify what's going on. Let me redraw part of that section up there. So what's happening now is this. What I'm going to see is the channel's going to begin to narrow at this end because the drain is now becoming more positive. So as VDS becomes more positive, then what I find is I get a stronger reverse bias between the drain and the substrate. So this is more positive, this stays ground, and therefore I get a larger reverse bias between the drain and the substrate, or between the drain and the bulk connection. So between my drain and my bulk connections, now what I see is this. With a larger reverse bias, I get a larger depletion region. And as the depletion region grows, it starts to narrow the channel on this end. So what I see is now the channel is no longer fully symmetrical. Now as this voltage is getting larger and more positive, that channel starts getting narrower and narrower as this reverse bias increases and as this depletion region gets larger. Now current is still flowing. Current is still flowing through the channel. And the current will increase as VDS increases, even though the channel is beginning to narrow. Okay, now this process continues. I keep making the VDS more and more positive. So at VGS greater than the threshold voltage, and at this particular boundary condition, once VDS becomes greater than or equal to VGS minus V sub t, so that's a boundary condition I hit. Once I reach this boundary condition, then the channel completely pinches off at the end, at the drain end. So now I'm in this situation here. Now I've got this. So I get this pinch-off region where literally it pinches off completely at this end, at the drain end. once that drain becomes positive enough and the depletion region gets large enough. Now at this point, you might say, okay, well, Dr. Holman, once that happens, doesn't drain current stop flowing? Actually, it doesn't. Can current flow through a depletion region? Can carriers pass through a depletion region? Sure they can. It happens in diodes all the time, right? When current flows through a diode, a forward bias diode, it's still going through a depletion region. So even though we're basically a depletion region in this pinch-off region, current can still flow. And so that continues to happen. The carriers go from the drain through that region and into the channel and then keep flowing into the source. So drain current keeps flowing. The difference is this. Once the channel pinches off, if I keep increasing VDS, at that point it doesn't get any worse. In other words, once I pinch off, in effect, increasing the voltage beyond that point doesn't really change the geometry of the channel very much. So here, so ID still flows, but further increases in VDS does not change the geometry of the channel. So the channel geometry doesn't change as I increase VDS. But here's something else interesting that happens. Once I reach pinch-off, increasing VDS does not change ID. ID reaches a maximum value at pinch-off, and then that's it. It doesn't get any larger. So once I reach this pinch-off, then ID remains constant. I can make VDS larger, but it's not going to really affect the current. Of course, I want to clarify, I do have VGS still connected between the gate and the source terminals, just to clarify to everybody. Okay, once I'm in this region where I pinched off that channel, now I say the NFET is in saturation. The drain current has saturated, okay? It's not going to get any larger as I increase VDS. So the NFET is now in saturation. Okay. We note cutoff, triode or ohmic, and saturation. There are three different regions of operation that this NFET can operate in. And guess what? We're going to have to be able to distinguish between those three regions whenever we are deciding how to determine the bias of a circuit that has this transistor inside of it. Okay? Now, looking at this, does this look fairly common sense, the idea of creating a channel for current to flow through that channel? It's very common sense. That's why Lilienfeld came up with this idea in the 20s. Conceptually, people understood enough atomic theory to realize that this should work. You should be able to actually create a region to make current flow through a solid state material. They just couldn't get it to work. But they understood the theory, the idea. And so Lilienfeld, as I said, patented this back in the 20s. And during World War II at Bell Labs, They were trying to duplicate Lilienfeld's work, make Lilienfeld's device actually work, but they stumbled across a totally different way to make a transistor. But this was really what they were trying to do, was build an FET. Yeah?
We've mostly been looking at doing things in order, but if you turned on VDS before you turned on VG, what would it just eventually reach the same state?
It will. It'll reach the same state. So in other words, if I made VDS positive first but kept the gate turned off, then no current's going to flow. I've got to form the channel. But in this case, if I had VDS at a large voltage and then turned on VGS, I would go straight from cutoff directly into saturation. So the channel would form, but it would immediately be pinched off. Okay? So yeah, I'm just going through this to kind of show the different steps, but you don't have to turn on a device in this way. I mean, normally you would just apply the voltage and everything turns on at once. But how it transitions through the different regions of operation will depend upon the different biasing that's applied to the transistor. And we're going to see that later on ourselves. Okay, so any questions? Like I said, this is hand waving. Okay, if some of my colleagues were here, they would shake their heads because obviously I'm really not looking at this thing in any kind of rigorous way as far as how the equations are developed. But I just want you guys to have that picture. And it's a pretty straightforward picture of how this works. Yes?
I guess before the channel is created, there's technically no channel sort of drain, but after the channel is pinched off, there's no channel between the two.
Well, no. Well, once the channel pinches off, there's a depletion region here.
Right.
But there's a large potential between those two regions.
Yeah.
So that will cause current to flow through that region, even though it's a depletion region.
I guess his question kind of relates to if we put a very large VDS before the channel is created, is there going to be any current?
If you make a large enough VDS before the channel is created, you can literally create a strong enough electric field where it will literally punch through. Just like a diode would break down. It'd be like reverse breakdown. That's not really a desirable region of operation for a MOSFET. Okay. So yeah, you could. I mean, you can actually increase the voltage on any semiconductor device to the point where you'll punch through and create a current path that doesn't really belong there due to breakdown. But in this case, unlike a Zener diode, we never want breakdown to occur in a MOSFET. That is not a good thing. Yeah?
Why is the current in saturation constant?
Because what's happening is the current, as the current increases, the current is a function of the geometry of the channel. So it's a function of the gate source voltage and the geometry of the channel. And as we increase the voltage, what's going to happen is once this pinch-off region forms here, this is essentially a highly resistive region. And so we increase the drain source voltage, it's going to have relatively little effect on this current going through there. Now, it's not zero. Now, when I say it has no effect, that's not really true. There is actually going to be a slight increase in current, as you're going to see here in a minute. But to the first order, we say that the current remains constant. Yeah?
And is that because of the negative voltage on the source?
Yeah, the source is grounded. The drain has a positive voltage. So current just flows this way through it, right? It's 2112. So current flows, positive current flows from positive to the negative side. All right? Okay, so like I said, a picture. We've got a picture. Now, at this point, we stop because you know what I'm going to do now? I'm going to start giving you guys equations. We're not going to try to derive the equations. In a semiconductor physics class, you actually would spend time figuring out the equations that I'm going to just show you guys now. But that's not the object of this class. Okay, now, just to illustrate what's going on here, let me draw this. I'm going to do a plot of drain current versus VDS. So let's plot what I was just writing about a moment ago. When VDS is equal to 0, ID is equal to 0. No current's going to flow. Now I'm going to draw a curve. And this curve assumes that VGS is greater than VT. So you notice I can draw a different curve depending upon the gate source voltage. But in this case, I'm going to assume the gate source voltage is some value greater than the threshold voltage. And so as VDS increases, I'm going to travel up this curve. So in this region, as I increase VDS, the current's going to increase. This is the triode region. And in this region, VDS is less than VGS minus VT. And then I'm going to hit a boundary condition. And the boundary condition is when VDS is equal to VGS minus V sub T. And then once I pass that boundary region and my channel is in pinch off, then because of the large voltage drop across that pinched off region, I'm going to see that the current doesn't really change very much. And now for VDS greater than VGS minus V sub T, the current effectively remains constant. And we say that this is saturation. So down here, we go from 0 to some maximum value, and then after that, the current remains constant. Now, as I said before, we assume the channel geometry doesn't change at all. To the first order, that's true. But actually, yes, increasing VDS does slightly alter the channel geometry above the cutoff region. And what we'll find instead is, ideally, the current's constant. But in practice, we will see a slight increase of drain current as VDS gets larger. So it's not accurate to say the current remains completely constant. It will increase slightly. The channel geometry is not completely invariant. So this is our actual current. Now, let me ask you guys a question. Ideally, I've got a region where the drain current remains constant. Actually, I should draw this slightly better here. Hang on. Let's draw this that's a little bit more like totally flat. Okay. Let me ask you guys a question. This goes back to 2112. In this region, I can increase or decrease VDS, and ideally the current remains constant. So let's think about this. An element where the current remains constant no matter what the voltage is across it. What does this saturation region remind you of from circuits 1? Current source. Yeah, think about it. Isn't this behavior similar to a current source? It's a constant current regardless of the voltage between the drain and the source. And this is an important thing. In this region, in saturation, the MOSFET is behaving very much like a current source. Now, obviously, it's not a current source in the sense that it can generate energy or generate power. But I'm saying it acts like a current source in the sense that the current is independent of the voltage. So in that way, it's like a current source. So ID is independent of VDS. That's what I mean when I say it's like a current source. Not that I can generate energy or get power out of it. Okay? Now, here is the boundary. This is the boundary condition. So, whenever we, as we're going to see here shortly, whenever we start looking at circuits to determine which of these two regions we're in, what are we going to be examining? We're going to be examining the boundary condition. We have to do a calculation and determine which side this MOSFET is on by calculating that boundary condition and seeing what the drain source voltage is. Is it greater than or less than that boundary condition? So this is a bit more complex than diodes, but fundamentally the idea is the same. We're going to go and check that boundary condition to determine how we're operating. All right? Now, here is something too. Okay? Notice here, I've been calling this saturation. All right? You guys have heard the word saturation before. Where did you hear the word saturation? Oh, do you have a question? Now, what was your question?
Yeah, just before we move on, is the ID that you get, is it going to be the same max for a lot of MOSFETs, or is it just going to be?
No, it's going to be a value that depends upon the value of VGS and a couple of other parameters, including the width and the length of the gate. I'll show you that equation in just a minute. So yes, no, ID is not just a value for every, it's not the same value for every device. It's going to be specific for that device, given the bias conditions and the geometry. But anyway, saturation. Where do you hear saturation? Op amps. Was saturation a good thing for an op amp? No. When an op amp saturated, it quit working. I'm calling this saturation because in this case, ID, the value of ID saturates, and VDS doesn't increase. Saturation for a MOSFET is not the same thing as saturation for an op amp. Op amp saturation is very undesirable. When an op amp saturates, it doesn't work anymore. It's no longer acting like a linear device. Saturation for a MOSFET, on the other hand, this turns out to be the most desirable operating region for a MOSFET. Now, to confuse us even further, when we get to BJTs, I'm going to define yet another definition of saturation, which is totally different from these two definitions. Unfortunately, what you find is in circuit design, sometimes we run out of words, and we keep defining the same terms that means different things. There's no way around this other than you just have to get used to it and keep track of it yourself. But for now, when I say saturation, I'm talking about a good thing. As it turns out, this thing behaving like a current source in that region is a very, very good thing when we're building analog circuits. Okay, so given all of this, let's write some equations. I want to emphasize to you guys, these equations will be right in front of you on that equation sheet on the first exam. It's already on, you can look on Brightspace and look at that equation sheet right now. You're going to be given that on the exam. So you don't need to memorize any of what I'm about to show you, but you're absolutely going to have to know how to use these equations. In cutoff, the drain current's equal to 0. No channel is formed. In triode, the drain current is equal to this. In triode, the drain current is equal to K prime N W over L times VGS minus VT quantity times VDS minus VDS squared divided by 2. It's a mess, isn't it? Well, like I said, you don't need to memorize it. It'll be there right in front of you. And then in saturation, ID will be equal to K prime N over 2 times W over L times VGS minus VT squared. And as we said before, ideally, as we can see here, there's no VDS term here. So ideally, this is independent of VDS. This equation you'll see in the books is called the square law equation. And if you were taking a semiconductor physics course from Dr. Reed or from Dr. Shrimp, you would actually, over the course of this, actually derive that equation. You'd actually, from the first order physics equations, you'd learn how to derive that. Yeah?
Just to clarify, for triode it's Kn prime or saturation is K prime.
Oh, no, I'm sorry, it's the same thing. Excuse me, I just did not draw that very carefully. It's the same term. Okay? So, something I want to point out here. Triode and saturation. Note that if VDS is equal to VGS minus VT, and I plug that into here for that equation, so if I plug these into here, at the boundary condition, this equation transitions to that equation. So this just becomes VGS minus VT squared over 2, VGS minus VT squared, so minus 1/2, and there's the 1/2 term. So this becomes that at that boundary condition. All right. What is this K prime N here, or Kn prime, whatever? What is that? We give a name to this. We call this the transconductance parameter. And if you look at the transconductance parameter, notice width and length are dimensions. So width divided by length is unitless. I've got VGS minus VT squared, that's volts squared. But current is amperes. So in order to make the units balance, the transconductance parameter has to have units of amps per volt squared. Not exactly intuitive, but that makes the equations work. What is this equal to? Well, the transconductance parameter is a function of the following. Mu sub n times Cox, where mu sub n is the mobility of the electrons in the channel. What is COX? COX is gate oxide capacitance per unit area. And sometimes you look at that and say, capacitance, why does capacitance figure into this? Well, let's think about this for just a moment. Here's the channel. The channel is a conductive layer. We have gate. The gate is conformed of either metal or polysilicon, which is conductive. And then in between, we have silicon dioxide, SiO2. Conductor, insulator, conductor. What is that structure? It's a capacitor, really. You think about it. The gate, oxide, and channel looks like a capacitor. And that's where that COX term comes from. There is gate oxide capacitance per unit area. What is that capacitance per unit area underneath that gate? So it turns out that the value of that transconductance parameter is built into the geometry of the device and also built into doping levels and the fact that we have electrons flowing beneath the channel and the mobility of those electrons. Okay? Questions? All right. So normally, this number is just going to be given to you. I'm showing you this to show you what influences the transconductance parameter, but normally you'll just be told the transconductance parameter is this value, and that's all you need to know. Now, a couple other definitions before we go any further. Some terminology we need. There are two types of MOSFETs. Now, looking at an NFET, there are two broader classes of MOSFETs. And one is called the enhancement mode MOSFET. An enhancement mode MOSFET is one where the channel is off until you apply bias voltages and turn the channel off, or turn the channel on. So by default, the channel is off unless turned on. So what I just showed you guys, when I drew all these diagrams for you, I showed you an enhancement mode NFET, one where there was no channel until I made the channel form by applying VGS. But it turns out there's an entirely different class of MOSFETs called depletion mode MOSFETs. And guess how depletion mode works? By default, there is a channel unless you force it to turn off. Now, 30, 40 years ago, depletion mode and enhancement mode MOSFETs were both commonly used. Nowadays, the depletion mode has almost completely disappeared. Nowadays, almost all MOSFETs are enhancement mode, but you will sometimes hear people talk about depletion mode, and there are still some more exotic types of MOSFETs made with other materials that will still use depletion mode operation. But if you look at old textbooks and old books, old textbooks and old technical papers, you will sometimes see depletion mode devices referenced. So I just wanted to point this out. We're not going to be looking at depletion mode at all. This is very rarely used, but just wanted you to know if you ran across the word exactly what it meant. So it's rarely used today. So everything we're going to be doing is going to be doing assuming enhancement mode devices, which is really pretty much predominant to what we see today in modern design. Okay. Questions so far? So there are your equations up there. Let's do some more equations, more definitions before we go any further. Another definition. V sub OV. That is the overdrive or effective voltage of the MOSFET. And this is nothing more than VGS minus VT. So this is just another way of saying VGS minus V sub T. That's the overdrive voltage. Therefore, the NFET is saturated if VDS is greater than or equal to VOV. So typically, whenever I do things in class and write it in my notes, I just say VGS minus VT. I'm very explicit. But the book likes to throw in this overdrive voltage quantity. Personally, I don't like to define extra variables and extra definitions that they're not needed. So I just normally stick with VGS minus VT. It's very clear, and it's referenced right on the diagram. Questions? All right, so let's now talk a little bit about some other quantities here. Let's see, let's go back up here. Let's do it up here. Let's talk a little bit about the conductance or the resistance of the channel. Let's think about it. I mean, we form a channel underneath the gate. Well, that channel is not made of superconductor. It's actually going to have resistance associated with it. So how do we quantify that? Let's consider channel conductance or resistance when we're in the triode region. So let's do a little definition here. I'm going to define the conductance between the drain and the source. And again, I'm assuming I'm in triode, so the channel is formed. So GDS in triode is going to be equal to the change in drain current with respect to the change in drain source voltage. All right, pretty straightforward definition. So for triode operation, I'm just going to use the triode equation. So I'm going to take that derivative. I'm going to calculate the conductance of the channel, the derivative of drain current in the triode region with respect to VDS. All right, so if I calculate this, and I'm going to skip the steps for the derivative, you guys can all do those. But if I do that, I will get the following. I'll get this. And it's actually, if you look at it, it's actually pretty straightforward because I can actually break this into two parts, take the derivative here and the derivative there, and it actually very easily becomes that. So you can see for yourself, it's a simple derivative. Or I can say this is equal to K prime N W over L times VOV minus VDS. So in this case, I'm using the overdrive voltage definition the book uses. All right? Now, we note if VDS is small, if VDS is much, much less than VOV or VGS minus VT, in that case, I can say GDS will just approximately be equal to K prime N W over L times VGS minus VT. So for small VDS, I can just ignore that VDS term as long as it's much, much less than VGS minus VT. Now, while we're here, we need another definition because the book makes a distinction between what the book calls the process transconductance parameter and the transconductance parameter. And our book makes that distinction. Other textbooks do not. But once again, I want to try to follow what the textbook is doing. So just for the moment, before I go any further, I have another definition. The book will define something called K sub n without the little prime. And actually, this is a useful definition if you're talking about discrete MOSFETs, the ones you can like buy and use in the lab. But you don't normally see this definition used in MOSFETs on integrated circuits. But this is the transconductance parameter, which is equal to K prime N times W over L. This is the process transconductance parameter. So the book likes to make this distinction. And as I said, it's not a bad definition if you're talking about discrete MOSFETs, because you can't really vary the width and the length if you buy a MOSFET, you know, 3-terminal MOSFET and you're using it in the lab. But if you're doing the design where you can vary the width and the length, you're not going to use this. You will normally use K prime N. And some textbooks just ignore this term. Okay, but our textbook does make that distinction, so I want you guys to be clear that the book does distinguish between these two. So the book defines these differently. Now, I just want everybody not to be caught off guard. The difference is going to be that lack of that prime. Normally, we just call everything, we just call that the transconductance parameter. I'm not going to call it the process transconductance parameter. I'm just going to call it the transconductance parameter. So I just want to be clear about that. But it may be different in a problem in the book. Don't be caught off guard. On an exam, I will always use this I'll make it very clear. I will use the K prime N. I will not combine them together or bundle them together normally, but you may see that on some homework problems. All right, so given this definition, I can rewrite this just using the transconductance parameters defined in the book without the prime. And then the W over L just gets incorporated into it. So you'll see that equation in the book. I didn't want any confusion to arise. Okay. And of course, I can always, in each of these, say that this is approximately equal to K prime times VOV. And this is approximately equal to K prime in W over L times VOV. So I can use the overdrive voltage instead. And once again, just using the definitions from the text. Okay, now I've defined conductance because conductance was easily calculated given the fact we had a drain current equation. What's the resistance? Inverse of conductance, exactly. So RDS is therefore just going to be equal to the inverse of the conductance, which will be equal to 1 over Kn times VGS minus V sub t, assuming VDS is small. So assuming the drain source voltage is small, then that is my drain source resistance, 1 over K sub n times VGS minus VT. And once again, I want to emphasize, this is only valid for the triode region. Okay? Well, we're going to see this definition again. You're going to run across this in a couple of problems. Now, as we're going to see later on, we also have to think about what the channel resistance is going to behave like in the saturation region, but that's going to be a different problem. Okay? So, this covers all the basics for the NFET. What about the PFET? Well, next time we'll quickly do that. I'm going to sketch it. You're going to find that the PFET has the same equation forms, but the polarities of the voltages get switched around. Okay? So we'll see that next time. And then we will start working some problems with NFETs and PFETs.